We are excited to have you here. My name is Matthew, and I am one of the course staff and instructors behind the scenes for the Coursera and Udemy classes. If you're joining us from those, welcome. If you are with us from some other source, we're grateful to have you here as well. I'm going to let Professor Impey welcome you all, and then we'll get started with your questions. Make sure you post those in the chat. Just ask them once. I promise we're getting them, and we jump around to get a variety of topics and give everybody a chance to ask questions. So don't keep posting them over and over again. I promise you we'll see them.
Okay, welcome everyone. Thank you, Matthew. And this is the Q&A session for online astronomy courses, and topics across the subject are welcome. So go right ahead.
Excellent. So there has been a discussion on sort of YouTube and Twitch recently, I think a couple of weeks ago, or maybe it was last month. Derek from Veritasium, the science communication YouTube channel, made a video about how the one-way speed of light has never been measured and can't be measured. And so we only have ever measured the two-way speed of light. So technically, we don't know if the speed of light is the same in all directions. We just know that it's the round trip averages out to this amount. So I don't know if you've ever heard of this or thought about this at all, but can you talk about the challenge or the impossibility of measuring the one-way trip speed of light?
Right. So the speed of light is a universal constant. So it's important to say what the reference for the speed of light is. It's a profoundly important physical constant because in the theory of special relativity, it's an absolute quantity throughout the universe, regardless of your frame of reference. In other words, no matter what your status is as a moving object and moving observer on a spinning planet or in a spaceship or whatever it might be, as seen by someone else receiving your light signal, they will always measure the speed of light to be 300,000 kilometers per second, roughly. And that's universal concept means that space and time are malleable in the special theory of relativity. It is true that the speed of light on large scales can only be measured with a round trip. However, the speed of light is measured in the lab, and it's measured on more terrestrial scales where you do actually have point A and point B, and so you are actually measuring the one-way travel time of light across the laboratory, or actually between two disparate laboratories. So it has actually been measured in a one-way sense, but only on the Earth. Once you measure the speed of light beyond the Earth, you indeed, since we don't have any labs that are manned somewhere else, you have to use a round trip. The most classic example of that is the reflectors that were left behind on the moon by the Apollo astronauts, and we've been bouncing signals off the moon for almost half a century, and those instruments provide a way of measuring the speed of light on its travel to the moon, which takes about a fraction of a second actually in each direction. And certainly beyond that, we do not have a way of measuring a round trip speed of light. However, if the speed of light were different in different directions in the universe, we would know that because we would see manifestations of that in looking at astronomical objects in different ways, in different directions. So it is maybe a little loophole in the laws of physics that we can't measure the round trip time or speed of light in both directions on cosmic scales. However, we've seen no data from the universe that would lead us to suspect that the theory of relativity is wrong in that regard.
Excellent. The next question is from the previous session that I thought was interesting, and I wanted to pose again for you here. Can you talk about nuclear propulsion and how nuclear propulsion would work for space travel?
So to go beyond the solar system, we really do need different methods of propulsion. Remember that everything we do in space is still using chemical energy. It's just using advanced versions of rockets that we've had really since Goddard's time, which is almost a century ago that the first liquid chemical rocket was developed by Robert Goddard, late 1928, I think. Things haven't really changed. They've become more efficient. And so we now have rocket fuels that are extremely volatile hydrocarbons. Hydrazine is the classic one that's used for retro rockets and small boosters and orientation rockets throughout the solar system and space probes. And then the big rockets use liquid fuel, liquid chemical fuel, but it's chemical energy. To go beyond the solar system, we're going to need a more efficient mode of energy production. And indeed, nuclear fusion or fission are hundreds of thousands or millions of times more efficient in terms of their energy released per gram or kilogram of fuel than chemical energy. And so people have hoped to have some form of nuclear fusion or fission reactors in spacecraft to send them beyond the solar system. The problem is, as we know, we have not harnessed fusion on the Earth at all in a fusion reactor, so that technology is simply beyond us, even on the Earth, let alone in space. And fission reactors are enormous beasts that weigh thousands or tens of thousands of tons, and miniaturizing a fission reactor is quite difficult. Basically, you use radioactive materials as power sources for especially probes that are far from the sun, so they can't use solar panels. But that's not the same as fission. That's just harnessing the energy from disintegrating heavy nuclei. That's not the same as fission itself. There are designs for fission reactors. Project Daedalus was a famous project going back, I think, to the 1950s, from Britain, in fact, which hypothesized how you might have a miniaturized nuclear reactor for a spacecraft. One of the designs, the more modern, slightly more modern design of this, involves making small nuclear explosions, essentially detonating very small miniaturized nuclear bombs behind a spacecraft and using a massive shield as essentially a deflector, where you essentially harness the energy released from the explosion to kick the spacecraft forward, and you just make an endless series of miniature nuclear blasts to push the spacecraft forward. It sounds very crude, but it's actually a possible technology that we could one day do, maybe within a few decades. But otherwise, these technologies are at least a few decades away. And for fusion-generated power in space, that's way far off, because we would have to be fully in command of that technology on the Earth before we could imagine miniaturizing it and using it in space. So I suspect that's a century off. It's unfortunate, because that's what we will need to leave the solar system.
So kind of a related question that's from Tianis Kuto, who's on with us live. And the premise of the question is incorrect, but we can address that. So how does graphite accelerate the chain reaction of nuclear fission?
Right. Actually, graphite does the opposite. So graphite is a moderator. Nuclear reactors with fissile material are usually embedded in water or as a coolant. And they also have typically graphite rods that are used as moderators, because essentially when radioactive nuclei decay, they release neutrons, and those neutrons continue a chain reaction of more decays, and that's what generates a lot of the power. When you want to slow down this process, you actually have to slow down the neutrons, and graphite is a very good way to absorb neutrons. So these graphite rods are inserted into a nuclear reactor. They're there all the time, and you can drop more in as needed to shut down the nuclear reaction. It's a sort of fail-safe on a nuclear reactor. So graphite is used to moderate a fission reaction, and it's used routinely in power stations that are based on nuclear fission.
Excellent. Kylie Hoying is looking to go into aerospace engineering and astronomy, but doesn't want to feel underprepared. I'm not sure if this person is a high school student or a college student, but what kinds of things do you recommend to help prepare for a career in aerospace engineering and/or astronomy?
They're both interesting, and they are somewhat related fields, but academically the paths are somewhat different, because astronomy is almost always in a college of science, and aerospace is almost always in a college of engineering. And those colleges at a big university are always distinct. At some universities, they're combined. But those are different pathways. Engineering programs have accreditation. They have a whole set of requirements. There's sort of base courses you take as an engineer that you would not take as a general science student before you specialize in one subject. So unfortunately, aerospace engineering and astronomy are academically quite distinct subjects. It's not really possible to combine them. And in terms of the background you need, for astronomy, you just need a strong background in math and, if you can, at high school level in physics. For aerospace engineering, it's about the same. You need a math background and a good general science background. Engineering is not typically taught in high school. So the engineering curriculum for aerospace is self-contained, and the specialization towards the aerospace aspects usually come later, because you need versions of mechanical engineering and other forms of engineering before you can get to an aerospace application. So they're really quite different career paths. And so you'd have to see what it is, what's the kind of job you visualize for yourself, what kind of work environment would you like to be in before you make a choice between those two, for example.
Excellent. The next question is from Sharp Tail Girl, who's on with us live, who would like to know estimates for the number of stars in the Milky Way and a number of galaxies in the universe differ widely. What numbers are you comfortable with?
They do, and it's important to know why they differ widely. It's not because astronomers don't know how to count or don't know how to measure these things. In terms of the number of stars in the galaxy, our galaxy, for example, it really is because the vast number of stars are low-mass stars, and those are very faint, intrinsically faint stars. So the lowest mass red dwarfs, which outnumber stars like the Sun by factors of hundreds to 1, are also thousands or tens of thousands of times dimmer than the Sun. And so it's very hard to count stars in the galaxy down to the red dwarf limit. The fusion limit is about 8% of the mass of the Sun, a very cool red star. And that's the real reason, that if you're doing a sheer census of stars in the galaxy, the vast majority of them are dim and faint red dwarfs. And so you're not actually counting them directly. You're sort of extrapolating based on the distribution of stars. So you need to know the relative numbers of the dim stars relative to stars like the Sun to get the right number. And that's why you'll see numbers that vary between maybe 200 billion and 400 billion for the Milky Way star content. It really depends on how you estimate those faint red dwarfs. And for the number of galaxies in the universe, it's a slightly different situation. For them, it's also because the galaxies we see out in space, especially billions of light years away, are the most luminous. We can easily detect the most luminous galaxies and not so easily the faint dwarf galaxies. But once again, there are many dwarf galaxies for every galaxy like the Milky Way. And so counting galaxies in the universe also depends on extrapolating to this large, very faint population, most of which you don't detect very easily with telescopes. So you're having to do an extrapolation or projection through a volume of space. And that's why the number of galaxies in the universe also, you'll see numbers that vary by a factor of 2. This is the reason.
The next question is from an email. El Ravi Narasimhan asks, the detection of phosphine on Venus seems far from settled, let alone its role as a biomarker. So how did such a paper with such extraordinary claims make it past Nature's intensive review process if it didn't have equivalent proof? They've read apparently that science rejected it prior to Nature accepting it.
Mm-hmm. That's a good question. The phosphine result is controversial. The team that published that result have not retracted it. They've not officially and formally retracted their result or that paper. They have, however, admitted that there's possible contamination in terms of the region of space where they saw this phosphine line, which meant that some fraction of its strength could be attributed to other elements, and therefore they overestimated the abundance of phosphine. They still claim that there's phosphine or there's a spectral signal that they think is still there after this debate that has to be attributed to phosphine, but it's at a much lower level. And it's at a low enough level now that, of course, the biogenic implication of it is now drawn into question. While it's not clear how you would get phosphine without biology involved, because on Earth, phosphine is always implicated or associated with biology, when it's at a very low level, you have to be very cautious. For example, methane on Mars. The debate over methane on Mars, which is at a level of a few parts per billion. That is thousands of times less abundant than on the Earth, where it's produced by decaying vegetation and cows and ruminating mammals and so on, is also up for grabs. People are not sure that methane on Mars represents biological activity. And it's the same with phosphine. As for how a paper could get through that might be, in fact, wrong, the reviewing process, even with Nature, which typically uses 3 to 5 independent referees, is not perfect. The people writing the paper made a fairly convincing argument. There's new information come to light, which again has muddied the water, if you like, and reduced the significance of the result, but not made it go away entirely. This paper's had a lot of scrutiny, so I think if the result ends up being wrong, it will be because it was independent. People tried to independently confirm it with better data and were unable to, and that hasn't happened yet. So again, the result is still sitting there as a result, the paper not retracted, the result not withdrawn, and so we're going to have to wait a while to see if the mud in this water clears.
The next question is from Rentgen 101, who may be able to clarify a little bit in the chat. The question is fairly specific, which is, can you talk about what happens to a large water ice meteor, like several kilometers size range, as it enters a thin atmosphere like that found on Mars? And then maybe you can talk about more generally what happens to meteors that impact Mars's atmosphere versus something on Earth.
Well, if the question is about an icy meteor or sort of a meteor that has a large water or frozen ice or volatile component,
yeah, it seems like water.
Yeah, so there are indeed interplanetary bodies that are rocky and some that are more heavily composed of ice, and that variation can be quite large. There are interplanetary bodies that are maybe 70% frozen water and frozen carbon dioxide and other volatile materials. If an object like that entered the Martian atmosphere, a couple of things might happen. First, a lot of that volatile frozen material would be ablated, would be boiled off. And so the asteroid or the incoming object would be reduced in size, even in the thin Martian atmosphere, because the incoming speed would be so large and the energy deposited in its surface by friction with that Martian atmosphere would be so large. It's also possible that since these bodies, which are heavily composed of water or frozen gases and liquids, don't have the structural integrity of a pure rocky asteroid, and so it could break apart. It could fall apart like a comet Shoemaker-Levy did, falling into pieces in the tidal forces of Jupiter's atmosphere. So if it's held together by the frozen liquids or gases, it could indeed disintegrate, and then the smaller pieces would be ablated and very little might get to the surface. So the outcome of a frozen water object or frozen ices object would be quite different than that of a rocky one, and it might not even survive the passage into the Martian atmosphere.
The next question is from Wendy Traver, who sent an email. If the effect of dark energy is not diluted with the universe's expansion, does this suggest that it didn't originate in the Big Bang?
The origin of the dark energy is still up for grabs. So it's not even possible to answer that question. It's a good question. It's not possible to answer it at the moment. All that we know is that dark energy does indeed have the quality where its strength in any volume of space, any co-moving volume of space, as we would say in astrophysics, is constant. And that means as space-time expands with the universe expansion, the strength of that dark energy doesn't change. Dark energy seems to be a product of the vacuum of space. It's generated by the vacuum. And so, in fact, as you make more vacuum of space by space-time expanding, you make more dark energy. And that sort of accounts for why its absolute strength stays the same. And that, of course, distinguishes it from dark matter, the other mysterious ingredient of the universe, because dark matter we think is a particle, and as space expands, the dilution of that fixed amount of dark matter increases, and its gravitational strength decreases, and so its influence gravitationally reduces. So dark energy stays in its influence on the universe and in any region of space at a constant strength, whereas dark matter declines in strength. As for whether it was part of the Big Bang, it seems like it must have been, because the space-time that's currently accelerating in its expansion due to dark energy originated in the Big Bang. So even if we don't know the exact mechanism whereby dark energy arose, it does seem to have arisen in the Big Bang.
The next question is from Student McLeod. What is the typical wattage of the transmitters that send Mars data to Earth? And is the frequency of the transmissions a secret so that ordinary people cannot record the data?
Mars, the electrical transmissions from Mars, or signal transmissions from Mars, have to be done fairly efficiently. On Mars, there could be, there's solar power available on Mars, but again, it's further from the sun than the Earth, so the availability of solar power is quite modest. And so every use of energy or power on Mars by a rover or a lander is guarded. It's very carefully monitored. And so the largest amount of wattage I've ever heard of a transmitter from Mars is about 100 watts, and many of them are a lot less than that. They're using beamed emission, so they're focusing it at some level to diminish the way it disperses through space and increase the amount of signal. And the antennae that are used to detect this, which is sort of the deep space network, these deep space network antennas distributed around the world are very large dishes. They're almost all over 50 meters in diameter. Some are 100 meters in diameter. So they're the largest radio telescopes we have. And that's because it's a very feeble transmitter that's being used just to conserve power. The frequencies of these transmissions, I don't think they're actually secret. And so in principle, you could detect it yourself, but you'd need a huge aerial or a huge radio telescope to do so. So I think it's not because it's secret, it's just because the signal as it arrives on Earth is so weak that the average civilian is not able to detect it.
Thank you very much. The next question is from Jordan Stone, who sent an email. When do you think we will be sending the first asteroid mining or biomining missions?
Well, these missions are probably going to come from the private sector. So NASA doesn't have any particular plans, nor does any other space agency, to engage in space mining in the way that we might understand that. And so if this happens, it's going to happen from the private sector. And there are, to my knowledge, about a dozen private space companies that are making advanced plans for mining in space. Now, that mining in space could include the moon if eventually there's a lunar base. None of these companies have the means or the resources to create a lunar base on their own. They're assuming that eventually governments will put lunar bases in operation and they'll be able to piggyback on that activity. The big prize, of course, for mining companies is to harness the incredible mineral wealth of a near-Earth asteroid, a sort of half-kilometer sized asteroid that could be brought into a near-Earth captured orbit, an Earth-Moon captured orbit typically. It's several $1 trillion in rare earths and several $1 trillion at current market value of precious metals. So it's an enormous resource in one object. And that's the glittering prize that you can see people are quite excited about. And that motivates these companies to be making plans to, capture a near-Earth asteroid into a tame orbit, which means altering its trajectory, and then developing the infrastructure to mine it in situ as it orbits, and then somehow get that material down to Earth. Whether it gets purified in space or purified on Earth is not clear. It might have to be mined and resourced and purified in space because the mass of material is so large that it's unmanageable to bring it back to Earth. It requires too much energy to do that. The economics of these companies and these ideas are not clear. It's the business models are a little sketchy. They have to make assumptions, and it's not clear if those assumptions are justified. So given all those uncertainties and the fact that no space mining company has the resources to do this work on their own without help from government partners and big rockets of the kind that Elon Musk is building, I would say that space mining is 20 to 30 years off at the minimum.
Star Trekker would like to know, what do you think will be the most significant additions to astronomy infrastructure this decade?
Well, the biggest additions to astronomy infrastructure are going to be these large new telescopes that are being constructed. So we are building the Giant Magellan Telescope in Chile, which should take first light in 4 or 5 years. The Caltech and the University of California and other international partners are planning the 30-meter telescope also, which is destined currently for Mauna Kea, but it's not clear if it can be built there. Plan B is to go to La Palma and the Canary Islands. And the Europeans have the extremely large telescope, a just under 40-meter dish, which will be also in Chile. So those 3 huge telescopes all should be finished within the decade. James Webb Space Telescope, of course, is due to go up at the end of this year, and it's be the largest space telescope by far. Those are the big infrastructure projects. Each of those ground-based telescopes is over $1 billion. James Webb is probably 10 billion at this point. So they're the most expensive resources. The other big astronomy infrastructure project is the Square Kilometer Array. That's a radio astronomers jump forward by a factor of 100 from the Very Large Array or any other radio array. It's a set of tens of thousands of radio telescopes distributed across Australia and the southern part of Africa. Their test arrays already have been constructed, consisting of a few hundred telescopes now. The technology of the receivers is moving forward, and that also will probably be finished within the decade. So those are the big projects of astronomy. There are also ideas for supercomputers, extremely powerful computers that can carry forward some of the simulations that astronomers depend on. Those computers have other uses, though, so they'll be doing physics, weather forecasting, climate modeling, and so on.
Water the Cow would like to know why Mars rovers don't create balloons to survey the land around them, kind of like weather balloons.
Oh, well, they could. Mars rovers could, and actually, that's an interesting idea. They could deploy balloons or aerial vehicles. The reason we don't need it on Mars is that Mars is extremely well served by orbiters. I think at the moment there are currently 3 orbiters around Mars giving extremely detailed information. One of them is mapping the surface down to the level of about a meter-sized objects, the entire surface. Another one is monitoring the atmosphere very sensitively. And of course, we have new Mars missions arriving right this month. So Mars is actually well served for objects in orbit that are essentially monitoring the atmosphere, the weather, dust storms, looking at geological features, and just doing general mapping. So we don't need the rovers to do that work.
Bob G. Donaldson would like to know, why do we not see an impact from dark matter in our solar system?
Well, it's just very difficult to do a dark matter detection experiment within the solar system. So if dark matter is a universal material or substance, which constitutes 6 times more mass than normal atoms, the kind we're made of and all stars and galaxies are made of, then indeed it is in the solar system too. It exerts gravity on itself and with other types of matter, but it's far less clustered or structured than normal matter, especially on the scale of a small part of a galaxy. So it's going to be fairly smoothly distributed. And that means the density of dark matter particles within the solar system where we might detect it is very low. So it's a very difficult thing to detect. And so there have been attempts to detect dark matter. And of course, the main dark matter detection methods are on the Earth itself, where we put detectors in deep mines and look for the occasional interactions of those detectors with dark matter particles that are around us and through the solar system and so on. So essentially, we're looking for dark matter in the solar system by the way we detect it on the Earth.
The next question is from Camila, who's on with us live. What do you think about the possibility of quantifying time or looking at quantized time? So, the way time passes in the quantum world, can we is there such thing as quantized time, and what would we learn from that, or what effect would that have?
It's an interesting question because it would have quite a big implication if time were quantized on any level. So we can just ask it as an experimental question, is there any evidence that time is quantized or discrete at all from experimental physics? And the answer is, at the moment, no. In the sense that we can design experiments which define very small intervals of time, say the passage of light between two adjacent atoms or something like that, defining times that are of order of picoseconds. And there's no evidence in any of those experiments, those sort of electronic microscale experiments, of discreteness of time. In other words, the variable of time in miniaturized experiments where light is the messenger, it appears continuous. There's no sense of discreteness of time. It's not quantized at the level, say, of picoseconds, which is a trillionth of a second. There is a hypothesis, of course, that at the level of quantized gravity, the time dimension could be quantized and discrete, but that's at a very much smaller level or interval of time than we can currently access with experimental methods. So it's on the table as a possibility, and some unified theories of physics do actually posit that time has a discrete or quantum aspect, but it's far from being measurable by current experimental apparatus that we have available to us.
The next question is from Surajit is here, and the specific question is, how can one pursue astrobiology after doing a bachelor's degree in life science? But maybe more generally, you could talk about how does one pursue astrobiology after a bachelor's program?
Right. So most astrobiologists doing graduate work or beyond have started in astronomy or planetary science. Could equally be planetary science, although that's a smaller field than astronomy. And typically they will start taking some life science courses as graduate students when they're doing their coursework and mixing it in with the physics and astronomy. It is possible to go into astrobiology, absolutely, from the perspective of biology. It's also possible to go into astrobiology from a geology bachelor's or from planetary science, of course, would be a natural one, or even oceanography. So there are various pathways into astrobiology at the graduate level, because astrobiology at the graduate level really only has maybe a dozen significant programs around the country. PhD programs are still quite rare. There are a few online master's programs. So the number of programs supporting graduate work in astrobiology is quite small, and they tend to be quite flexible in what kind of students they take, and they tend to have fairly self-contained courseworks. So if you came into astrobiology from a biology background, they would provide through an astronomy department foundational astronomy and maybe physics courses to address deficiency in that area, and so on. So I think you just have to find the astrobiology graduate program that might interest you, and they will see what the requirements are, and you will find that the people who run those programs tend to be, with a good student, a student who performs well as an undergraduate, quite flexible in the requirements and look for ways to get you into the program.
Excellent. Kind of continuing on the theme of careers in astronomy, Amina Hajieva would like to know, are aerospace engineering and astronautical engineering jobs at a drought? Are they overpopulated or being taken over by robots? What's the future for astronomy and engineering jobs related to astronomy?
Well, engineering jobs related to astronomy are doing quite well, because astronomy has some very large projects that are heavily dependent on very state-of-the-art engineering, mechanical, electrical, electronic. It's a whole variety of modes of engineering to make these large telescopes, or spacecraft instruments, or telescopes for space. So there's a set of astronomy research projects that use engineering skills quite heavily. Aerospace engineering is a particular career track, and it has had its ups and downs in the last few decades. I think currently it's doing quite well, or the recruitment in that area is doing quite well. And that's partly because the aerospace, the sort of main aerospace sector has come out of a bit of a slump. And also because now we have something like 24 private space companies that are hoping to compete with Blue Origins and SpaceX to actually get a real activity going in space. Now, there's still a small number of companies in an absolute sense compared to other parts of the industrial sector. So the total number of jobs is not enormous, but it is a growing region. So space engineering is growing. Aerospace at the moment is growing. And engineering associated with large astronomy projects is growing because there's some very big billion-dollar astronomy projects that hire quite a lot of engineers, not just when they're being constructed, but also to operate them.
Excellent, thank you. Our next question is from Mover and Shakers 707. Could you please explain what the Hubble tension is?
So the Hubble tension, that phrase, if you see it in the news or in the media, refers to the fact that there's a disagreement between the measure of the Hubble constant based on local expansion rate of the universe, that is the local Hubble constant, and the Hubble constant measured or inferred through measurements of the microwave background. So that's early universe measurement of the expansion rate. Now, if we have a cosmological model, that model should predict what the expansion rate is and how it changes over cosmic time. And so with a model, in other words, knowing what the ingredients of the universe are, you can say what the Hubble constant, it's not a constant because it's changed, that's the expansion rate at any given time, how that Hubble parameter, to be more correct, has changed over time. And the problem is that the local or nearby or recent measure of the expansion rate is not agreeing with the more distant measure of the expansion rate. This disagreement is only at a level of about 5 or 6%, but actually the data is now good enough that that is a problem because these two measurements tend to disagree by more than their error bars, which means the probability that they are inconsistent given their quoted errors is small, less than 1%. And that means 99% probability there's a problem, and that's the Hubble tension. How this gets resolved is not clear. It could get resolved at either end of the disagreement. In the local distance scale measurement, it's also a problem that when we measure the local universe, we have to assume that our local volume where we measure the expansion rate is typical. And there's large scale structure in the universe, enormous structures and voids. And if you don't pick a fair sample of galaxies, you can get a skewed result of the expansion rate locally. And people are still arguing a bit over that. And there's also a chain of methods that are used to measure the expansion rate locally. Typically, Cepheid variables are involved. And so miscalibration or misunderstanding of the physics of the Cepheid distance scale could lead to an error. The people who do this work claim there's no error at the level of 5 or 6%, but it's not clear. There's argument about that. At the high redshift end or the early universe end, the problem is that you don't actually formally measure the expansion rate directly as you do in the nearby universe. You measure it in a combined sense through a cosmological model by measurements of the microwave background radiation properties. And so there the uncertainty is whether you've used the right cosmological model. So at the moment, the tension has not gone away with new data in the last year or so. Seems to have persisted, maybe even got a little sharper. Some people are saying there's a bigger problem here. There's something problem with the physics or with the cosmological model itself. Other people not willing to go so far are just taking a wait and see attitude. But I think we'll know the answer to this interesting conundrum within the next year or two because people are working very hard on this problem.
The next question is from Silverfrost 712. Do you think that international space law is comprehensive and effective or lacking?
Well, it's actually lacking. It's a little niche. I would call it a growth niche. It's a small niche, of course. We have not a whole space law concentration at the University of Arizona, but we have more than one course on space law, and it is a specialty that you can do at the University of Arizona Law College. And there are a number of law schools around the country and internationally where space law is on the curriculum, and it can be taken. And I think there are even a few space law programs in Europe where that's the entire concentration. But space law is an emerging field because space law is governed by essentially only two international treaties, the Outer Space Treaty of 1965 and the Moon Treaty of 1979, both United Nations, signed by varying numbers of countries, but a large number of countries. And those treaties deal with nuclear weapons in space, and they deal with certain aspects of ownership of property, but they are mute to private sector players. They only really talk about governments, governmental agencies. And so there's a whole set of space law that has not yet been created to deal with who owns what, who can claim ownership of extraterrestrial bodies, who can claim the property rights and the mineral rights and the resource rights, what kind of regulations you can impose over citizens who live off Earth. This is another huge area of law that's not resolved because it doesn't arise yet. Nobody is living off Earth except for very short periods of time. So space law is a very small but a growing field, and we can look at the future of space travel and predict that in a few decades it'll become a significant thing. So it's something to keep an eye on, and it's probably not a bad bet. I wouldn't say you could make an entire living in space law reliably if you went into it right now, but if you hedge your bets and had another specialty as well, it might be an interesting way to go for the future.
And the next question is from Oxbowman. How will we address the problems of radiation exposure in long-term space flights to Mars? And is the human journey possible at all given this hazard?
Yeah, radiation exposure on a long mission to another planet is a serious issue. The most rapid, reasonable trajectory to Mars is about an 8-month trip in space, subject to radiation exposure. Remember, you're also going to have exposure on the planet Mars itself, but there presumably there'll be a habitat that's protective. The reason the exposure in space is worse is because the cost of going to Mars depends heavily on mass, and the more massive you make your spacecraft, in other words, if you put a lot of heavy metal shielding in to protect the humans, you'd make the cost prohibitive. So essentially, spacecraft are just thin metal shells with not a lot of cladding or protection, and so the humans are heavily exposed. The estimate is that on a trip to Mars, you get about as much total radiation exposure, maybe a little more, than a whole human lifetime on the Earth. That sounds like a lot, but it's actually, again, only doubling your total radiation exposure. It's increasing your rate of cancers by tens of percent, 30 or 40%, depending on the type of cancer. So it's an increased risk, but it's not a terrible risk. The worst risk would be for much longer journeys through space of more than a year, or for sojourns on a planet like Mars without suitable protection, again, for periods longer than a year. So at the moment, the space radiation risk for what we're planning in the near term is manageable. It's an extra increased risk, but the truth is, on a human flight to Mars, there are other risks that are actually far greater than the radiation risk.
The next question is from Water the Cow, who would like to know how far would people have to travel to leave the galaxy?
Well, that's farther than we can really contemplate at the moment. The easiest way to get out of the galaxy is to go straight up or down out of the galactic plane. Remember, we live in a spiral galaxy in a disk. We're actually slightly on one side of the disk, so if you were going to leave the galaxy itself and be able to look down on the disk, for example, you'd go out in the direction on the side of the disk that we are slightly skewed towards. The thickness of the disk is only a few hundred parsecs, so I think a distance of about 1,000 light years would take you significantly outside the disk of the galaxy. The density of stars would diminish. From that perspective, it wouldn't look dramatically different. You'd be outside the plane of the Milky Way, but not very far outside the plane of the Milky Way. So to the eye, it would still seem like a Milky Way extending as a band across the sky, but maybe filling half the sky instead of just a strip. So the answer is about 1,000 light years. That, of course, is a distance far larger than we can contemplate at the moment. It's a distance that's hundreds of times larger than the distance to the nearest star. So that's a long way off.
The next question is from Photozone. And I think there are kind of two questions buried in here. Could dark matter simply be small or even larger black holes that we do not see? And could these black holes be tiny, and some have formed shortly after the Big Bang?
So the idea of black holes as dark matter is an interesting proposition, of course, because black holes are dark or black. They're only black if they're not surrounded by material or part of a companion with another star that we can see. That's how we detect black holes that are dead stars. So there are two possibilities. The black holes for dark matter, they could be just dead stars, and those are massive stars that die as supernovae and leave behind objects that are 3 or 4 or 5 times the mass of the sun. We can rule that out very convincingly for dark matter because any such set of massive stars that died as supernovae would create enormous debris, glowing debris, shells of gas that are heated up, glowing X-rays for hundreds of thousands or millions of years. And so the black holes might be dark, but the pyrotechnics that precede the formation of the black hole be easily visible. And to have enough black holes to make up the dark matter, we can just rule that out very easily. Small black holes are a little harder to rule out, and they tend to be called primordial black holes. So as part of the Big Bang theory, there's the possibility that out of the extremely dense space-time in the early universe, you could have small pockets where the density was high enough to form black holes, and you get a spectrum of tiny black holes called primordial black holes, essentially arising from the Big Bang. Now, the smallest of those black holes, assuming Stephen Hawking is right, would have evaporated by Hawking radiation, and so there'd be no evidence of them 13 or 14 billion years later. But if they were massive enough, and then they only go up to a certain mass because the universe is expanding and you don't get to create a certain size of black holes. So it turns out there's a little window in there where the black holes could exist. They could be big enough so they haven't evaporated by Hawking radiation in the history of the universe, but not so big that we'd see them in other ways, or that the universe had been able to make them before it got too diffuse. And that's the window people are trying to rule out. At the moment, it's still possible, in principle, that primordial black holes constitute the dark matter, but that window of availability for them to explain it has been diminished a lot in the last 10 years by experiments and astrophysical observations. And so it's almost ruled out that primordial black holes are the dark matter, but not quite.
And so kind of related to that, can you give us a sense of the scale of the dark matter problem? Like, I mean, there's a lot of dark matter missing. And so, the solution isn't going to be simple, right? Like it's not just going to be, a lot of one thing or, a lot of some big obvious thing like black holes, because you'd think we would have seen or find evidence of those because there's tons of dark matter. Can you give us like a sense of the scale of that problem?
Sure. I mean, there is an enormous amount of dark matter, and and it's easy to put a number on it. I mean, the number of normal particles, which is to say protons and neutrons, electrons are 1,000 times smaller, so we don't need to count them. But the number of protons and neutrons, and most of the universe is hydrogen, so we're really talking about protons. The amount of normal matter in the universe is 10 to the power 80, 1 with 80 zeros after it, protons. That's how many protons there are in the universe. Now, dark matter, we know on all scales, and especially largest scales, outweighs normal matter by a factor of 6. So we need, if there were particles as massive as protons or neutrons, we need 6 times 10 to the power 80, or that enormous number of dark matter particles to explain the dark matter. And if the dark matter is composed of larger objects, you just can put those particles together with almost 10 to the 81 of them and figure out how many objects you need. So you can rearrange the dark matter from fundamental particles into bigger objects, but the bigger objects are actually easier to rule out because you have to find a way to make them if they're black holes. And like I said, that's ruled out. If it's small objects like pebbles or dust grains, they get irradiated by stellar radiation and glow in the infrared, and we don't see that infrared glow. So those particles are ruled out. And really, we're down to subatomic particles. So the requirement on dark matter, since there is so much of it, is that it has to be a particle that in physics terms is just as abundant as protons and neutrons, and a little more so, obviously. So, it can be some super rare, exotic, esoteric particle that happens very occasionally or through some very rare interaction, because there's got to be as many of these particles as there are the normal particles that we're made of. And that kind of cuts your option down quite a lot. And that's why the best bet still is from some supersymmetry type theory where there are shadow set of particles from the mergers of forces of nature that mirror the normal particles we see, and that would automatically essentially give you about an equal number of the dark matter particle.
All right, it is 1:51. We have a time for one, possibly two questions, but we'll definitely squeeze one last one in here. The next question is from Pelotil Hugh. The question is about Enceladus. The jets of ice and water spurting from those tiger stripes are called by some astronomers geysers, and other equally professional sources as cryovolcanoes. Is there a difference? And if so, what is the difference between a geyser and a cryovolcano?
Yeah, these are technical terms. A geyser, well, on Earth, a geyser is a place in the Earth's surface where water is ejected into the atmosphere for various reasons. Now, that reason for ejecting a geyser could just be pressure, building up that releases episodically. It could be driven by volcanism. It could be driven by seismic activity. So there are a number of mechanisms to create a geyser. A geyser is just the fact that water is ejected out of the surface. And in Enceladus, these icy particles are not water because they freeze instantly going into the vacuum of deep space far from the sun. And so that's the description of the geysers. Cryovolcanism is sort of a mechanism. It's a different thing entirely. It's a geological term that relates to the release of energy within a planetary or a lunar type, moon type object caused either by volcanism, tectonic activity, or just by natural radioactive heating from decays of radioactive elements in the deep rock. And if that energy release is sufficient, it can drive, it can, of course, create liquid. It can create a surface of liquid under a frozen surface, and that energy release can also drive the liquid up through the surface, and cryovolcanism can indeed lead to a geyser. And so cryovolcanism could be going on in Enceladus, caused in that case by the tidal heating from the planet Saturn. So cryovolcanism is an interior mechanism of heat generation and heat transmittal through the interior of a moon or a planet. And the geyser is a sort of manifestation of water as it is forced out from the surface through gaps or crevasses.
All right, I think that's going to be the last question for today. We have to wrap up because we have another meeting pretty soon. I just want to say thank you to everyone for joining us, and thank you to Victoria, who's running our stream with us behind the scenes and helping out with questions. It's a big help.
Yeah, thanks, Victoria and Matthew, and we'll announce the next two sessions before the end of the week, and I'll be back with you next week.